Hello everyone. So we are discussing significance of poles in a control system. So if we have the poles of a transfer function, then what information we can get from these poles we are discussing. So in last lecture we studied if we know the poles we can find the stability of a system. Now in this lecture, we will see about time constant tau of a system and frequency of oscillations of a system. That means if you know the poles of a transfer function, you can find the time constant tau and the frequency of oscillations. So let us start with the time constant tau of a system. Now there are two methods to find the time constant tau of a system. First, the time constant tau is given by minus 1 upon negative real part of pole location. So this is an important formula you can write in your notes. So the time constant tau is given by minus 1 upon negative real part of pole location. Now this formula is valid only for stable system. So this is again one important point you need to know. First is the time constant tau is given by minus 1 upon negative real part of pole location. And second important thing is it is valid only for stable system. So this was one method to find the time constant tau of a system. There is one more method for finding the time constant tau. We can use the standard representation of a time domain equation, and the standard representation is e raised to minus t by tau. If you have an equation x of t, you can compare your equation x of t with the standard equation e raised to minus t by tau. Then you can compare and find the value of tau. Now we will look in some examples so that it will be clear for you. And one more important thing is that the time constant tau is always a positive real number. The time constant cannot be a negative, so a time constant tau is always a positive real number. Now since we have understood these two methods, let us solve some examples so that it will be clear how to find the time constant tau. So the first example, I have a transfer function x of s which is given by 10 upon s plus 2. First, we will find by method 1 using time constant tau formula. The time constant tau formula is minus 1 upon negative real part of pole location. Here the minus sign is important and here negative real part of pole is important. Now in denominator we have s plus 2. If you equate s plus 2 is equal to 0, you will get the pole s is equals to minus 2. Now if the pole is negative, then only we can find the time constant tau, because here we have written negative real part of pole locations. So if you substitute the value, it is minus 1 upon the negative real part of pole location. Negative is minus and the pole is at 2. So the time constant tau is given by 1 by 2 seconds for this question. So this is very simple analysis. Now since the pole is on left hand side of the S plane, it is a stable system, and for stable system we can find the time constant tau. Now let us consider the same example, but here we will be using the standard representation method, that is to compare with e raised to minus t by tau. So I have this x of s which is 10 upon s plus 2, and to get the equation x of t, I have to take the inverse Laplace transform. So I have to take the inverse Laplace transform. In our earlier lectures, we have already discussed how to find the inverse Laplace transform. So the inverse Laplace transform of 10 upon s plus 2 will be 10 e raised to minus 2t u of t. Now we have to compare this 10 e raised to minus 2t with this e raised to minus t by tau. So if I compare both this, e raised to minus 2t is equal to e raised to minus t by tau. Again from here, tau will be equal to 1 by 2 seconds. So again, for the same example, we got the same answer, which is 1 by 2 seconds. So these are the two methods to find the time constant tau of a transfer function. Now let us consider one more example. I have the transfer function x of s is pi upon s minus 2, and we are using the method 1 time constant tau formula method. We know the time constant tau is given by minus 1 upon negative real part of pole location. So if I substitute s minus 2 is equals to 0, you will get the pole s is equals to 2. Now if you substitute the value in time constant equation, you will get minus 1 upon negative real part of pole location. Pole is at 2, so it will be minus 1 by 2 second, and you have guessed it right, it is a wrong answer. The first thing is s minus 2, the pole is not a stable, it is unstable because it lies on the right hand side of s plane, and we have written negative real part of pole location. We have got the positive part. So we have not got the negative part. Our pole is s is equals to 2. It is not s is equals to minus 2. Hence, this answer minus 1 by 2 is a wrong answer. So we have proved time constant tau is only applicable for a stable system. Now we have one more example. Example number 3. Our transfer function x of s is given by 10 upon s plus 2 into s plus 3. Find the time constant tau. Now again, we know the time constant formula. Tau is equals to minus 1 upon negative real part of pole location. So if I want to find the pole, I have first pole S1 will be minus 2 and S2 will be minus 3. Since we have two poles, we will be getting two time constant. So I will write tau 1. So tau 1 will be minus 1 upon first pole is at minus 2. So it is minus 2. So tau 1 is equal to 1 by 2 seconds. Similarly, the second time constant tau 2 is equal to minus 1 upon negative real part of pole location. It is minus 3. So I can write minus 3. So the tau 2 value will be 1 upon 3 seconds. Now we have got two time constant tau 1 and tau 2. Now if you have been asked to find only one time constant, then the correct answer is 1 by 2 seconds. Now why this 1 by 2 second is correct and why not 1 by 3 second is correct? This concept is called dominant pole. So your s minus 2 is a dominant pole as compared to s plus 3. Our next lecture will be on dominant pole. In that lecture, you will understand why time constant t1 is the correct time constant. So we have two time constants. Both these time constants are correct. But if you are asked only one time constant, then tau 1 is equals to 1 by 2 second is the correct answer. For this, we need to study the dominant pole concept. Our next lecture will be our dominant pole concept. So I hope you have all got a clear idea about the time constant. Now our next point is frequency of oscillations. Now if you know the pole location, you can tell the frequency of oscillations. To understand this, let us consider one example. I have a transfer function x of s which is given by 1 upon s square plus 1. Now the inverse Laplace transform x of t will be sine t u of t. So the plot of sine t u of t we have already studied in the last lecture. This is the sine t u of t, and we know when the signal is sinusoidal, it is marginally stable system. So we know sine t ut is a marginally stable system. Now since the system is marginally stable, if you are told to find the time constant 1 upon s square plus 1, if you have this transfer function, there is no time constant since it is not a stable system. Sine t u of t is a marginally stable system. and time constant we find only for stable systems. But we can find the frequency of oscillation for the given transfer function. Now let us see how to find the frequency of oscillations. I have taken the same transfer function x of s is equals to 1 upon s square plus 1. Now we have two poles. First pole is plus j1 and the second pole is minus j1. The plot of poles on S plane is as shown. We have one pole at plus j1 and the second pole at minus j1. Now we are interested in finding the frequency of oscillations. The frequency of oscillations is the imaginary part of the pole location. So the imaginary part of pole location is your frequency of oscillation. Now we have the pole S1 is equals to plus J1. You can also write it as real part is 0, 0 plus J1, and you can write this as 0 minus J1. So the real part is 0, and we know the frequency of oscillation is the imaginary part of pole location. So the term which has J is your imaginary part. So the imaginary part is 1. So the frequency of oscillation is 1. Again, same like time constant tau, the frequency of oscillation is always a positive real number. Now let us take one example where we find both the time constant tau and frequency of oscillation. Now consider a transfer function x of s which is given by 1 upon s plus a whole bracket square plus b square. Now if you find the poles, our first pole S1 is minus a plus jb and our second pole is minus a minus j. Now you can plot this on the S plane. So I have first taken this real part is minus a, then I have plotted this pole at minus a plus jb and the second pole at minus a minus jb. Now first we will find the time constant tau. It is nothing but minus 1 upon negative real part of pole location. So the pole is negative and the real part is a, so I can write minus a. So the tau will be 1 by a second. Now we have already discussed poles on left hand side, but if they are complex and still if they are on left hand side, then also our system is a stable system. So since this is a stable system, we can find the time constant tau and frequency of oscillation. We know the frequency of oscillation is the imaginary part of the pole. The imaginary part is B. So the frequency of oscillation is B. We have one chapter in control system called as stability analysis. In that chapter, we will discuss a method called Raoult's-Hurwitz criteria to find the stability. In that chapter, we will require this frequency of oscillation. We have some good questions on frequency of oscillations. We will discuss these questions when we study the chapter stability analysis. Now let us take one more example. I have x of s is equals to 10 upon s square plus s plus 1. Now if you plot the poles, I have s1 is equals to minus 1 by 2 plus root 3 by 2j and s2 is minus 1 by 2 minus root 3 by 2j. You can plot these poles on the s planes. Now these poles are complex, but they are on the left hand side of S plane. Hence, this is a stable system. And if you find the time constant tau, it will be minus 1 upon negative real part of pole location. So negative real part is minus 1 by 2. So minus 1 by 2. So the time constant tau will be 2 seconds. Similarly, the frequency of oscillation omega naught, we know it is the imaginary part of pole location. The imaginary part is root 3 by 2. So the frequency of oscillation is root 3 by 2. So this was the concept of time constant tau and frequency of oscillation. So if you know the poles, you can find the time constant tau of a system and you can find the frequency of oscillation of a system. So our next lecture is an important lecture and it is on the concept called dominant pole. So I would request not to miss this lecture. It is an important lecture. So see you in the next lecture.